Hello everyone, my name is ABIODUN-OJO of Market Study Consult. Today we are treating another topic that is applicable in both electrical and electronic circuits, connection of resistors. Resistors can be connected in series, in parallel, and combination of both series and parallel. This is applicable in every electrical and electronic circuit. That is what we are treating today. As mentioned, we have three ways that resistors can be connected. We have the series connection, parallel connection, combination of series and parallel connection. All these are applicable in electrical and electronic circuits. What we are looking at here, there are resistors 1, 2, 3. It depends on the number of resistors you are connecting. There is different loads that you are connected together, not just one resistor like we used to know the color band resistor. They are called loads, but it can be in series and it can be in parallel. Take for example the lamp in your room. 2, 3 different rooms can have lamps. A room or a sitting room can have 3, 4 lamps, depends on the size of the sitting room. How is the lamp being connected? Is it in series? Is it in parallel? These are what we are learning here. We have resistor 1, 2, 3 here. When you want to calculate the total number of this resistor, the total resistance is as you see connected now. We have R1, R2, and R3. The total resistance is addition of all the resistance. They are like chain 1, 2, 3. That is R1 plus R2 plus R3 plus as many number of resistance that are connected. They are combined together to make the total resistance of that circuit. So we call RT, that is the total resistance, as R1 plus R2 plus R3 plus to as many number of resistors plus Rn, that is the number of resistors that are connected. Sometimes be more than 2, maybe more than 3, and that is what the Rn represents. So if this resistor has values now, whatever value it is, 1 ohms, 2 ohms, 3 ohms, everything will be added together. Example of what we are doing, let's say that this resistor has 2 ohms, let's say R1 is 2 ohms, R2 is 3 ohms, and 5 ohms for R3 respectively. So it means our R3 will be equal to 2 plus 3 plus 5, which is equal to 10 ohms. As we have been taught, ohms is the unit of resistance. Looking back to our Ohm's law, I said that the applied voltage in any circuit is directly proportional to the current and inversely proportional to the resistance at a constant temperature. So the unit of that ohm, which we are seeing here, is the ohmic value of that resistor. And I, which we are seeing here, is the current, while this is the voltage. The voltage that we know is measured in volts. I, which is the current, is measured in ampere. All this combined together makes the circuit work. The ohms is spelled as OHMS for somebody who may be new to this course, but some of the people that we have taught, because the combination of the lecture, so we have already been taught this in the past, that ohms is the ohmic value of the resistor. This is how to calculate the value, total value of that resistor. There is something important that we need to know. In series circuit, the current is common. What do we mean by the current is common? That is, when this current is flowing, it's like a chain. As you can see, the current flows through here from R1 to R2 to R3, and the circuit continues like that. From here, flows like that. The arrow is showing that, going and until the circuit is complete. One disadvantage of this kind of connection is the fact that, let's assume that this R1 has problem, it's faulty. Let's say this leg is cuts off here, or it cuts off here. Once this R is having problem, the current will flow, but once there is problem here, let's say there's an open circuit or the resistor is bad, you should be sure that this resistor will not work. The remaining two will not work again. But once the circuit That is why we say that the current is common. That is, the same current that flows from here is what we are seeing flowing all through. The voltage will be divided according to the value of the load, and that the voltage drop across each load. These are the characteristics of series circuit. We have that the current is common. When you say characteristics of series connection, So you have that one, the current is common. That is, the same current will flow all through. We have the potential difference, which is the voltage drop. The voltage drop across each, depending on the value of each resistor. We have voltage drop across each resistor. Which means the voltage will drop between here and here, will be V1, between here and here will be V2, between here and here will be V3, which means you won't have the same voltage flowing. The voltage here will be for this, voltage here, which is 1, 2, 3. Addition of all the voltages will make the applied voltage from this cell or the battery. So you have your V1 plus V2 plus V3. Depends on the number of resistors. But voltage is never common. Current is the only one that is common here. And on and on like that. As time goes on, when we go to some other topics, you will see where all this will be applicable. By the time we are doing the calculation of both series and parallel, then you will see the application of this. And this is where we call it that the voltage will be shared. And in parallel, in series circuit, you will use what we call voltage divider rule. We apply voltage divider rule, and that is what this means. Because the voltage will be divided, that's what I mean by voltage divider rule. Let's go to parallel connection now. Here we have our parallel connection of resistors, R1, R2. So as many numbers of resistors we have, it is connected in parallel this way. Compare this one to the previous one we treated, series connection. We can see that in series connection, the voltage applied, current flows, but it flows like a chain from 1, 2, 3 to 2 to 3 to 4 as the case may be. But in this case, we apply current divider rule. The other one, which was the series resistor, the voltage was divided. But in this case, the current divider rule is applied in parallel connection. As you can see, I flows this way. Look at that arrow. And when it gets to this junction, it will be divided. Look at the arrow. Some current flows to here. Some current also flows through the second resistor. The connection here, the implication of this parallel connection is that compared to the other one that is series, if there is any problem with this resistor or with either of the resistor, lack of functionality of this one will not disturb this. That is, when the current gets to this junction, current flows and the circuit can still be completed through here. If it is this one that is faulty, only this one will not work, but the current will flow through here like that, and the circuit can still be connected and the functionality will still be okay. And that is why when you have your sitting room, you will see that when a switch is controlling two lamps, you will discover that when one lamp is off and the other lamp is on, you'll be wondering, as a layman, but as an engineer, you know what it means. That is, you go and check if one of the lamp is bad and you change it. But if it is series connection, the two will go off because they are in chain. But this one is not like that. And how do we calculate the total resistance in a parallel circuit? we have it as it's a reciprocal. Let's remember our own law that says that voltage applied in a DC circuit is proportional to the current and inversely proportional to the resistance. We are applying it here now. So we are calculating our total resistance as 1 over R1, 1 over R2, and 1 over R3 as the case may be for the number of resistors. So our 1 over R3 is equal to 1 over R1 plus 1 over R2. So invariably when we want to do it, we see that reciprocal is what we are doing here, but by the time we say our RT will be equal to R1 times R2 divided by R1 plus R2. That is the total resistance. Unlike the series circuit that you add the resistance 1, 2, 3, 4 as the case may be. So it will still be the same thing here to the number of R. That is 1 over R1 plus 1 over R2 plus 1 over Rn, the number of resistors that is used. That is what this means. So if you have more than 2 resistors, more than 3 resistors, you are still applying the same formula. Let's just quickly do 1 or 2 examples. The value of this resistor now, as we have it here, what is this one? R1. What is this other one? R2. So what we are saying here, if this one is 5 ohms and the other one is 2 ohms, what we are doing here is we are calculating the total resistance of this one and this. Let's say it is 4 ohms. So which means we have RT. Our RT will be equal to R1, R2 divided by R1 plus R2. So we are saying that it's equal to 5 times 4 divided by 5 plus 4. If you use your calculator to do that, you will get your value to be 20 over 9, and that is 2.2 ohms. That is the total resistance of that circuit on the board. Then there are some characteristics for parallel connection which I've also mentioned, which is different from the series. We say that current is common in series circuit. For parallel circuit, it is voltage that is common. That is, the whole voltage that is flowing here is coming here. So which means if you have 10 volts, for example, the same 10 volts will be here, the same 10 volts will be here. Is the current that will be divided according to the value of the load. And the lowest resistance will carry the highest current. The higher resistance will also carry low current. That is, in parallel circuit, the characteristics is we have 1, the voltage is common. The voltage is common. So here, current divider rule is applicable. Current divider rule is what we use. We use current divider rule. Then 3, current divider rule that we use shows that you have each current, the IT will be equal to I1 plus I2 plus I3, that is till the number of resistors you have, which means the current here will be added to the current here. It will make this total current that is flowing here. Because if this one is flowing like this and it branches to this plate, it branches to this plate, by the time it flows there, the combination of it eventually meets again. So which means the total current here is a combination of the current that branch here and comes back to complete the circuit. That's the meaning of this one. That is, the current will be across each load. And under this place, we don't see any fault that will affect the two load at a time. It will only affect one. So that is for
the other one, the parallel connection. All of these are the foundation that will be applicable, and that is why you should get this right, because in this video you continue to use this. The Ohm's law will be applicable, the current divider will be applicable, the voltage divider will be applicable. Like I mentioned when we started this course, it's not just resistor that you used to know, not just the color band resistor, but this is indicating nodes of different values that you can see in electronic circuit. So we are going to another one, which is the combination of both parallel and series connection.
As you can see, we have series parallel combination here. These two resistors, R1 and R2, looking at it, they are connected in series. Then R1, R2, they are in parallel to R3. This combination of series and parallel. Likewise, the other one, R1, R2 are connected in parallel in series to R3. So both are still combination of series and parallel. Parallel series connection, parallel series connection, respectively. So our rule of series will be R in series, R series will be equal to R1 plus R2, then in parallel with R3, which means we are going to say our R series, we have 2 plus 4 ohms, which is equal to 6 ohms. Then, because the two, they are now in parallel with R3, our drawing will now change to this. We have this, we have this. So our parallel connection is out, which is the short form. The combination of this, which is 6 ohms, the combination of this, which is 4 ohms. So you now have our total resistance for this whole circuit will now be, so let's go to this side. RT will now be 6 times 4 divided by 6 plus 4. That is RT. We have 6 times 4 is 24. 24 divided by 10 will give us 2.4 ohms. Going to the other side, because R1 and R2 is connected in parallel, you have R1, R2 over R1 plus R2, which gives us 2 times 2 divided by 2 plus 2. You have 4 over 4, this is equal to 1 ohm. 2 times 2 divided by 2 plus 2 gives us that. Then we now have this. The shade will still come back, our shade of series circuit. So you have this now, which gives this 2 ohms plus and 2 ohms give us 1 ohms as parallel circuit. Our 4 ohms that was there before, we now have our RT equals to 1 plus 4. That is equal to 5 ohms. So the total resistance for this is 5 ohms. The total resistance for this 2.4 ohms. You can see something. You will discover that when resistors are connected in parallel, the combination of the two resistors will give us a lesser ohmage value. You can see 2. Look at the value give us finally. By the time we added it is when you now do the series connection that it now increase the value. Now look at this one. It was series before. It's now connected in parallel. You can see that the ohmage value increases when it is series. When it's now connected in parallel, you can see the value. It has now dropped to 2.4 ohms. So when you want a higher current to flow, the lower resistance will carry the highest current. And when the resistance is high, the the current will be reduced. So whatever connection you are going to employ will be depending on the parameters of the circuit you are designing.
That is why you need to know all this. When do you need connection in parallel? When do you need it in series? When do you need to combine both parallel and series connection? Let's quickly go to an example that combines series and parallel, and then we are going to apply our Ohm's law to calculate the current, the voltage, and even the power in such circuits. As you can see, we have series and parallel connection. We want to calculate some values that will bring us to the knowledge of how to calculate power in this circuit, the application of current divider rule, and voltage divider rule, which we have learned in the past. According to our Ohm's law, that the voltage applied is directly proportional to the current and inversely proportional to the resistance. All this will still be used here. Previously, we learned under parallel circuit that the voltage is common, which means this applied voltage is common to parallel circuit. But because the series resistor is connected, the 30 volts will not flow directly to this parallel circuit like we know the other time. Because of this one that is in series, some part of the voltage will be here, some will be here. But one fact is that the quantity of voltage, the value of voltage that is here, will be the same for both R1 and R2. So because of that, if we are able to check this, we know how to calculate R. The first question says calculate the value of R. This can be applicable in a situation where a designer wants to know the calculation of which resistor will be needed to work out this circuit. Or let's say prevention, you lost the resistor in the course of faults and you can't trace the value. If you are able to know some other surrounding components with all the variables, you can know the value of that resistor that is missing or that is faulty there. Even if the worst comes to worst, let's say you don't even have the technical manual for whatever reason, which I don't think it's possible, but let's say you don't have it. These are where all this could be applied. Now, the current flowing here, as I mentioned during the series and parallel connection when we did this separately, under the parallel connection, the current flows this way and it will share. So, which means if you're able to know the voltage across this resistor, since voltage in parallel circuit is common, it is the same voltage that will be applicable here. So, the combination of the voltage of this and this comes here, with the voltage of this one will be shared. So, current divider rule, voltage divider rule will be applicable. But here we are applying the current divider rule because some current flows here, some current flows. And we also apply voltage divider rule here, which shows that at this junction, you have a voltage, some voltages that will be here. From here to here to it will be another voltage. So with our VT here will be equal to the V across here plus the V across here. Combination of this and this will make the two voltages to total to 30 volts. So how do we get the value of R? First of all, we must know the current across here, which is 1.5 volts and 1.5 ampere multiplied by this. From our Ohm's law, recap, V is equal to IR. Don't let us forget, under Ohm's law, let's remember this triangle that we were taught. We have our V here, we have our I here, and we have our R here. Let's assume that you want to calculate V. It means the voltage is current multiplied by resistor. Let's bring it out, IR. Voltage is highly proportional to the current and inversely proportional to the resistance. Now, because we are calculating I now will be equal to, let's say we cover this, V over R. So we have our V, I will be equal to V over R. And let's also cover R here. Cover R, we have V and R. So our R will be equal to V over current. So what we are applying here now is showing that we want to calculate voltage. What is the applied voltage? The current applied is 0.5 multiplied by 20. So this one will give us 10 volts, which means the voltage across between here and here will be 10 volts.
V1 is equal to 10 volts. Now, that is the same voltage that is common to both. Now, how do we calculate the current? For us to calculate the current, we already know that our calculation of current is I is equal to V over R. V over R. But before we do that, the only thing that is common is current in series circuit. Where do we have series circuit? This is our series circuit. We cannot do this combination for now because we don't know the value of this side. So we continue, we come to this side to get the current, which means whatever total current that is across this resistor will be the total current across the circuit. Let's look at it this way. This voltage is applied, current is flowing. By the current flows to this way, we don't know the value yet. It shares. We already know this one, but we don't know the value yet. But technically, we know that when this current shared here, it will be equal to coming here, then going here. Which means the total value of the current here is what we have across this 5 ohms resistor. So which means whatever voltage and current we are able to calculate across this resistor is the total voltage that is coming here. So it is easier for us to calculate the current across here, showing that that is the total current across the circuit. So because of that, we are going to use this value to calculate the current across it. And the current across it, we first of all know the voltage, which is our 30 volts. So having known our V1, we already know that the applied voltage is 30. So for us to know the voltage across it, we get Vt. From Vt is equal to V1 plus V2. So our V2 now will be 30 minus 10. So V2 will be equal to 20 volts, which is the voltage across here, V2. So as I already know this V2 now, that will make it easier for us to know the value of our R. But we have not known the total current. So for us to know the IT will be equal to V over R. And because we already know the voltage across here, current and voltage across here, and the resistor, our IT is equal to I in series. I is equal to V over R, which is 20 volts, divided by 5, which is equal to 4 ampere. So we are through with that. Now, how do you know our 4 ampere? Don't forget, the current across here is 0.5. 0.5 ampere is applied to this resistor. We don't know the current here, but we have already known the total current. Addition of this is equal to the current across here. So which means our VT or IT is equal to I1 plus I2. So I2 will be equal to IT minus I1. I2, which is the current across the no resistor, is equal to 4 minus 0.5. I2 is equal to 3.5 ampere. So once you already know the current across this resistor, to know the value is easier because you already know the voltage. So value of the unknown resistor, value of R is equal to V over I, which is equal to the 10 volts across the resistor because it is parallel circuit, voltage is common, divided by 3.5. R is equal to 2.86 ohms. To calculate the power absorbed, which is question number 2, we have our formula as P is equal to V times I in words. P is equal to V, which is applied voltage, multiplied by the total current which we calculated. P is equal to 120 watts. We can also use some other formula which you can do on your own. As your assignment, P is equal to V squared over R, and you can also use P is equal to I squared times R. Do that one on your